All right. Hello, everyone, and welcome to part 10 of Learning Rust series. Today, we're going to be looking at structs. I created a Rust book, project, or whatever they're called, in my general Rust projects directory, Rust book, by typing in cargo new Rust book here in my PowerShell. If you haven't downloaded PowerShell, you can download it from Microsoft's website. It's different from Windows PowerShell or the command prompt. It's pretty good. I mean, I like it so far. Anyway, okay, so structs. I've actually gone through this and read the chapter before making this video. Structs are like dictionaries in Python, or hash maps in general. Let's read. A structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. So it's a collection like tuples and arrays and stuff, but you can name each of the values, basically. So it contains key value pairs. If you're familiar with object-oriented language, a struct is like an object's data attributes or fields, going from C#. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions. Okay, called methods. Look at that. So structs are like, I guess, classes, maybe, to specify behavior associated with a struct type. Structs and enums are the building blocks for creating new types in your program's domain to take full advantage of Rust compile time type checking. All right. Defining and instantiating. Similar to tuples, they hold multiple related values. Like tuples, pieces of a struct can be of different types. Unlike with tuples, in a struct, you'll name each piece of data so it's clear what the values mean. Right? So a tuple was something like this, right? 0, 1, 2, something like that. That's a tuple. And a struct is down here. So it's a little bit different. Okay. To define a struct, actually, let's go back and look at the tuple type as well. Let top. All right, so that's how you define a tuple. Or that. The type inference is done automatically as well. Okay. So that's a tuple. Let top 1, 2, 3, something like that. If you want to make that a struct, I guess that would be looking at this syntax. You'd have to do struct top, and then yes, first is that, second this guy, and third is that guy. Another comma. Okay, that's the struct version. You're naming each of these guys, each of these values. That looks a lot like a dictionary in Python, or the JSON. Yes, JSON format. The struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets, we define the names and types of the pieces of data, which we call fields. For example, listing 5-1 shows a struct that stores information about a user account. Right, so that's the listing. Okay, is the user active? Takes a Boolean value, true or false. Username takes a string. Email, string, sign account. Yeah, I didn't actually do this. Like, I should have done something like this. I32, I2, and third is also I32. And then when creating a top object, whatever they're called, when create an instance of the tube here, I would then give it values. So something like that. Let top be a tuple, and then okay, that's very verbose. Okay, so I have to type all of these again. 1, 2, 3. Okay. I wonder if I can actually, if this actually compiles. So cargo run, C. No. Add that guy, okay. A semicolon at the end. All right, there we go. Number 14. Oh, I don't need to add one here. Do I? Yeah. Doesn't look like that thing requires a semicolon, but this one does, because it's an assignment statement. Fields in the struct. All right, so unused variable tube, unused variable tube. Fields for second and third are never read. What does that mean? Oh, okay, so they're never read by anything else. So this struct is never used. That's what they're saying. And they're saying is it in field by field basis. Not so some fields of the struct might be unused by your program. So that's what the compiler is warning about. All right. Okay, I see. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key value pairs. So these are key value pairs. That. Where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template with particular data to create values of the type. For example, we can declare a particular user shown in listing that 5-2. Okay, yeah, I did that here. To get a specific value from a struct, we use dot notation, like tuples. So tuples use dot notation here, like that. The 0 index element of the tuple, 1 index element, 2 index element of the tuple. And it's like that with structs. For example, to access this user's email address, we use user.email. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. So if you declare it as mutable, this guy, user1, which is of the user type, then you can change stuff here by doing this. User.email change to a string created from this string literal. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. Okay, I see. Yeah, that would be too tricky to manage anyway. Okay, yeah. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. We can construct a new instance of the struct as the last expression in the function body. What function? We're now into functions. Listing 5-4 shows a build user function that returns a user instance with the given email and username. All right, so it takes these of the string type, returns a user type, this function. And to return this, it just creates a user and returns this. Okay. Cool. You don't need to do this let something, 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 and then return that. You can just use this section here. Okay. That's cool. The active field gets the value of true, and the signing count gets value of 1. Yeah. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there is a convenient shorthand. Okay, so build user. Do you have to actually I think you need to define the struct outside this function, right? So can I do something like this? Struct, let me do this, user, and then I'm gonna get the, nope. I'm just gonna copy and paste this here. We'll get the tuple. Okay, we have a struct like this, and I am going to define a function. Build user. Email is going to be a string, and username is going to be a string. And it is going to return user. A user type, that is. And it's just building that inside here. Let's use the shorthand here, using the field init shorthand. Because the parameter names and the struct field names are exactly the same, we can use the field init shorthand syntax to rewrite build user so it behaves exactly the same but doesn't have the repetition of username and email. So this is how you do it. Username, email. There's also, okay, I see. So user active true, and then use username and email from the function parameters. And then signing count starts at 1. I think this is how you do it. And inside the main function, you can call build user. We'll first need a string from. It's going to be the email from x at y z. That's the email, and then another string from the username. And that's going to be, say that's the username. In build user, I wonder if this is going to compile. So let's try that. Cargo run. Yep, it compiled. It just has warnings. These fields are never read. Okay. And Rust book generate one warning. That's it. You're doing it. They're not read. Yeah, I guess that's how you can do it. Let me, nope. Do this. And if I have let user one get that, and can I print anything from here? User one email, for instance. Do something like this. Must be a string literal. Oh, missing a string literal to format with. Like that. So that's how you do it. Okay. How about this? That's how you use print line, I guess. Not supporting format string. Okay. Let's do it the way you suggest. All right, it did that. And it never actually prints the other fields. Of course, that's what the warning is about. I thought you could do this though, like put it in here. Why did that not work? I need to brush up on print line. Yes. All right, so email, and we have 0, and then say a new line, and let's do this. Active, new line, actually active user one, active. I wonder if this is going to work. Is there an implicit conversion there? Yep. So the bool type is converted into string literal implicitly. And let's do this. Username, and then email, sign in, out. User one, username, user one email, and then user one sign in count. Now let's do this. All right, no warnings anymore. And I was able to read from each of the fields. Okay, cool. Let's get this here and do that. Let's continue, I guess. We use the field init shorthand here. All right. Here we're creating a new instance of the user struct, which has a field named email. We want to set the email field's value to the value in the email parameter of the build user function. Because the email field and the email parameter, let's do this. Okay, do that. So it's more readable. Have the same name, we only need to write email rather than email. Makes sense. Creating instances from other instances with struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from another instance but changes some. You can do this using struct update syntax. So creating another user from user1's values. First, in listing 5-6, we show how to create a new user instance in user2 regularly without the update syntax. 5-6. Right. We set a new value for email, but otherwise use the same values from user1 that we created in listing 5-2. So this creates another user using user1's values, the fields, the values kept in those fields, and only the email is different from user1. Okay. Using struct update syntax, we can achieve the same effect with less code. So right there, that's the syntax. The syntax double period specifies that the remaining fields not explicitly set should have the same value as the fields in the given instance. Right. You only specify what you're changing, and the rest, get the rest from user1 by the struct update syntax. Okay. There is a caveat though. The code in listing 5-7 also creates an instance in user2 that has a different value for email, but has the same values for username, active, and sign-in count fields from user1. The double dot user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user1. So this must come last. And there is no comma here after this, by the way. If you're just specifying the fields like this, there's a comma in the last element, right? I think this is JSON format is like this as well. There's a comma at the end of the last element. But here, if you're using the struct update syntax, there's no comma after it. Okay? There's no comma after this. Okay. Must come last. Note that the struct update syntax uses assignment like an assignment. This is because it moves the data, just as we saw in the variables and data interacting with move section. In this example, we can no longer use user1 as a whole after creating user2. This is a caveat I was talking about. So you're moving all of this data to user2 when you do this. So user1.active is no longer going to be valid. It will be dropped after this move. Can we do this? Let me do this. All right. Let user1 build user blah blah blah, and then let's do let user2 use this one here. It's a user. Email is different. String from A at BC, B.C. And the rest comes from user1. Now, if I try to print user1's data again, I'm not going to be able to, according to this. All right, let's see. If I go run, add semicolon 13. Okay, sure. If I go run. Value borrowed here after move. Right. So Borrow of mood value, user1 username, and so on. So it's complaining I can no longer refer to user1 active username or sign-in count. I can refer to user2's values. This won't be a problem. Or go run, right? No problems here. But since this is an assignment, right, that assignment does not copy things, it moves things. You use another user, I guess, to create a new one. All right. Okay. Was moved to user2 if we had given user2 new string values for both email and username, and thus only use active and sign-in count values from user1, then user1 would still be valid after creating user2. Oh, okay, so it's only the interesting. Given user2 new string values for both email and username, let's only use active. Let's do that. Email, username as well. Username. It's just the username that's a problem. String from is that. And this is not going to be a problem, we're saying. Because assignment actually creates a copy of these U64 and bools. But string is another matter. Assignment does not create a copy of the string. That's why the borrowing thing doesn't work. If I go run, right, user2 is never used. That's the only warning, but it compiles. Right, because these types, the bool type and the int type, 64, these guys get copied implicitly when you do an assignment like this. Whereas a string, when you do an assignment with a string like username or email here, these guys are not copied. They are moved. Okay, sounds good. Are types that implement the copy trait. So those are traits that we're talking about. So the behavior we discussed in the stack only data copy section would apply. Rust also supports structs that look similar to tuples called tuple structs. Tuple structs have the added meaning the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples, and when naming each field as a regular struct would be verbose and redundant, or redundant. So they're halfway between a struct and a tuple. Tuple struct. Cool. Okay. Struct color. You use the struct keyword as well for these kinds of tuples. Struct point. Okay. XYZ color RGB. If that's obvious to the reader, and yeah, I can see these guys being used instead of a regular struct. Black origin. Okay. Note that the black and origin values are different types because they're instances of different tuple structs, right? So this is a type, this is another type. Each struct you define, even though they have the same type of objects or data populating them, They're named differently, so they're different types. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of 3i32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot followed by the index to access an individual value. Right? This structure is unpacking in Python terminology. Unit-like structs without any fields. You can also define structs that don't have any fields. Like that. No fields. These are called unit-like structs because they behave similarly to the unit type, empty tuple. Unit-like structs can be useful when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. We'll discuss traits in chapter 10. Here's an example of declaring and instantiating a unit struct named always equal. Function main let subject be always equal. Okay, cool. To define always equal, we use the struct keyword, the name we want, and then a semicolon. No need for curly brackets or parentheses. Then we can get an instance of always equal in the subject variable in a similar way, using the name we defined without any curly brackets or parentheses. Imagine that later we'll implement behavior for this type of struct that every instance of always equal is always equal to every instance of any other type. What? Behavior for this type such that every instance of always equal is always equal to every instance of any other type, perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. Okay, you'll see in chapter 10 how to define traits and implement them on any type, including unit-like structs. Okay, sure. I don't understand what this is. Ownership of struct data. In the user struct definition listing 5-1, we use the owned string type rather than the ampersand string. That's address of str, string slice type. This is a string slice type. This is a deliberate choice because we want each instance of this struct to own all of its data, and for that data to be valid for as long as the entire struct is valid. Okay, that's a fair argument. It's also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetimes, like the following. This won't work. Our username is an address of str, address of str. These are string slice types. And you're defining these for those with string literals directly. Compiler will complain that it needs lifetime specifiers. Missing lifetime specifier. Expected a named lifetime parameter. Okay. In chapter 10, we'll discuss how to fix these errors so you can store references in structs. But for now, we'll fix errors like these using own types like string instead of references like address of str. Okay. An example program using structs. Let's continue this in the next part of the video series.